Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are now starting our third lecture for our course of communication systems. If you recall, in our last lecture we talked about the concept of electromagnetic spectrum. Actually, the understanding of the electromagnetic spectrum is important because most of the communication systems they focus on any specific range of or band of the frequencies in the particular electromagnetic spectrum. So different applications, they are focused on different bands. In this regard, one of the important concept is that of bandwidth. So for today's lecture we'll start discussion with the definition of bandwidth, and then we'll move on to some related discussions. So the concept of bandwidth is actually applicable to both signals and the systems, because as we discussed in our previous lecture, whenever we talk in terms of communication system, so we will be dealing with two parts. One is the signal part, which actually has to be carried from the source side to the destination side, and second is the system, which refers to the actual hardware through which this system passes. So the concept of bandwidth is actually applicable to both of them, and of course there is a slight difference in the definition regarding the bandwidth of both of them. So whenever we talk about bandwidth, so we have to understand whether we are talking about signal bandwidth and the channel bandwidth. So first of all, the signal bandwidth is actually defined as the portion of electromagnetic spectrum which is occupied by a signal. So signal bandwidth is comprising of that particular frequencies which are representing that signals. Similarly, the channel bandwidth is actually refers to the range of frequencies required to transmit that desired information. So you can see that in both cases the bandwidth is actually referring to a range of frequencies. For signal bandwidth we talk about the range of frequencies that are occupied by the signal, and the channel bandwidth is refers to the range of frequencies which is used by the channel in order to transmit that particular signal. Actually we understand that signal has some time varying component. So generally the signal changes with time, and when the signal changes rapidly with respect to time, its frequency contents or spectrum, they extends over a large range. In that case the signal would be having a larger bandwidth, and if the variation in signal is slow, so the signal will be having a smaller bandwidth. Similarly, for the system point of view, because system has to accommodate those changes in the signal and it has to respond to those changes, so the ability of the system to follow the signal changes in response to the variation occurring in the signal is actually named as the transmission bandwidth. So the transmission bandwidth should be greater than the signal bandwidth in order to have a proper communication. So you should also understand that every communication system has a finite bandwidth, and of course that finite bandwidth limits the rate of variations that can be transmitted through that particular signal. So in other words, the bandwidth would determine how fast we can transmit the information through a specific channel. So the concept of bandwidth is primary to communication systems. In fact, this electromagnetic spectrum has become a precious natural resource. We know that we cannot transmit two signals simultaneously at the same frequency, because that will be causing interference in both the signals. So we have to divide the electromagnetic spectrum among different users so that they can transmit the signal without interference. And therefore the communication engineers, they make lots of effort to efficiently use the electromagnetic spectrum and represent the communication signals with a smaller bandwidth, so that most of the signals, they can be occupied in the finite spectrum. So there are lots of efforts going on between communication system to minimize the bandwidth requirements in order to transmit the given information, so that we can conserve the spectrum space and send as many as possible signals through that finite amount of spectrum. Also, because we know that we cannot make simultaneous transmissions on same frequencies, therefore there is a need of some spectrum management as well. Because if two users, they start transmitting at the same frequency, eventually none of the user will be able to have a successful transmission. So therefore spectrum management is a primary concern in all types of communication system. Generally the spectrum management is done by governmental agencies. So the entire electromagnetic spectrum is actually controlled by the relevant governments, and they allocate the spectrum to a specific users or specific type of application, so that each user transmits in its own spectrum. In the United States, there are different agencies which control the spectrum. Spectrum management is done by Federal Communication Commission (FCC) and the National Telecommunication Information Administration (NTIA). Similarly, we also have governmental agencies in Pakistan that provide the spectrum control and management services to different applications. In Pakistan, the spectrum management is done by Pakistan Telecommunication Authority (PTA) and Frequency Allocation Board (FAB). So whenever a user intends to have some sort of transmission, they first need to take permission from the PTA, and they get specific spectrum, so that they are able to transmit at that particular spectrum. Say for example, if someone wants to start a radio channel, so if someone wants to start a radio channel, he or she cannot transmit directly on any specific band. First they have to apply for a license from Pakistan Telecommunication Authority, and Pakistan Telecommunication Authority would allocate a specific frequency. Say for example, if Pakistan Telecommunication Authority allocates a frequency of, say for example, 105.8 megahertz. Say for example, if you are given a frequency of 105.8 megahertz, in that case you can only transmit in that particular band. So one radio can transmit in that particular band. If someone else wants to apply for a start of radio transmission, in that case he or she again has to apply for telecom PTA for a license, and then PTA will allocate a different band. Say for example, they allocate a band of 104.2, say for example. So he or she has to transmit in that particular band. So the bottom line is we cannot transmit at any frequency unless we get a proper license from the appropriate governmental body, which is Pakistan Telecommunication Authority here in Pakistan. And I would strongly recommend all the students to look at the Pakistan Telecommunication Authority website, because they have very good information related to telecommunication policies and usage in Pakistan. So that will be very beneficial for our telecommunication students. So you should look at that PTA website. Frequency Allocation Board is also an important organization who has the office in NED University as well, opposite to the NED Gymnasium. although it's restricted area and students and faculty, they are not allowed to go there without permission, but that frequency allocation board controls all the spectrum, all the transmissions that are made at different spectrums, and they keep on monitoring all the transmissions so that they can check whether if there is any type of violation or interference against the policy of PTA and FAB. So this is one of the important aspect of deploying communication system, that we need to incorporate spectrum management so that the spectrum is divided among different users and different applications. Another important aspect related to telecommunication system is the telecommunication standards, because there are number of applications of telecommunications and there are number of vendors and service providers which work on those applications. So there is very important to have a standardized system or standardized guideline to create the compatibility between different application. I give you a simple example. Say for example, if someone uses a Wi-Fi modem from some company, say for example you have a modem that is made by Huawei, and you have a cell phone that is made by, say for example, Nokia. In that case, because they are different manufacturers, if they are not compatible with each other, so they will not be able to communicate with each other. So it is very important to have some standardized specification that are common on the reception side, cell phone side, and the transmission Wi-Fi modem side, so that even if you use different vendors, equipments from different vendors, you are able to communicate with each other. So these standards, they are also developed by some international bodies, so that different manufacturers and different service providers, they make a compliance to those standards, so that different services, they become compatible with each other and we can have communication without any type of interruption. Generally these standards are developed by different groups. Some of them are ITU is International Telecommunication Union, IEEE, and 3GPP group, and so on. They are working on different apps, developing different types of standards. Okay, so far we have talked about variety of different phenomena related to communication systems, and now we can understand some fundamental limitations on the regarding the information transmission through a communication system. Previously we have talked about noise, because noise is an unavoidable phenomena which always resides in the communication systems. So no matter what you do, you have to face some sort of noise in the system. And second important limitation that we have talked today is the bandwidth, because bandwidth for any application is limited. So you have to use you have to make the transmission and in that particular bandwidth. So these two are the fundamental limitations related to communication systems. So how much information you can transmit through a specific channel or a specific medium depends on these two parameters, that is bandwidth and noise. So the question is how much transmission information rate we can transmit. It is addressed by a scientist named Shannon. He proposed a law in 1948, and he stated that the rate of information transmission cannot exceed the channel capacity, which is given by the formula here, which is C is equal to B log to the base 2 of 1 plus S by N. You can see that this formula incorporates the effect of both the limitations. This B represents the bandwidth and S by N is the signal to noise ratio, so it represents the effect of noise. So combining these two limitations, we can get an important parameter which is named as channel capacity, which is the maximum possible rate of information that can be transmitted through a system. For convenience of student, because most of the calculators, they do not have function of calculating log to the base 2, I have transformed this formula into the in another log, which is common log to the base 10. So if we transform this formula into this form, log to the base 10, so we will get this as 3.32 into b log to the base 10 of 1 plus s by n. So through this formula we can calculate that how much maximum capacity a channel can support whenever we intend to have some sort of transmission from the channel. This law is named as Hartley-Shannon Law, and this is actually provides an upper limit on the performance of communication system. At this point I want to mention that this law, the derivation of this law, although I haven't talked about the derivation, but it assumes some specific conditions. Firstly, the noise is assumed as the random Gaussian distribution, and secondly we assume that the information is randomly encoded. So after, if we have some different types of coding scheme, so we may have a different capacity formula for other types of applications. Okay, so with this we try to take a simple problem. So consider an AWGN channel with a 4 kHz bandwidth. So we are given the bandwidth, and the noise power spectral density N0 is given as 2 into 10 to the power minus 12 watt per hertz. The signal power required at the receiver is 0.1 milliwatt, and we want to calculate the capacity of this channel. Okay, before solving this problem, because there are some new terms which are used in this problem, so let me first describe those terms and then we'll move on to the solution of this problem. So first of all, as I previously explained, that capacity is actually the maximum information rate that can be transmitted through the channel. Generally the capacity is represented in bits per second, or sometimes we call it information bits per second. There is an abbreviation used here, AWGN. AWGN stands for additive white Gaussian noise, and you understand that we have used additive white Gaussian noise because the property of noise is that it gets added to the system. Gaussian represents a distribution of noise that follows the Gaussian distribution. White, the term white refers to the constant power spectral density of the noise. So what is an AWGN channel? AWGN channel is actually a simplified representation of a channel. Is a very commonly used in the analysis of communication systems. In AWGN channel we consider that there are no adverse effects from the channel other than the noise. So there is only one adverse effect, which is noise, that affects the propagation of a signal. So in that case the received signal is represented as sum of transmitted signal and the noise. So the output signal will be sum of two things. One is the transmitted signal and noise. So we have only one adverse phenomena, which is noise. Another term which is used in the problem is power spectral density. So the term power spectral density is actually represents the spectral distribution of power. So actually it's defined as the power per unit bandwidth. So it is not the power, it is actually power divided by the bandwidth. So it's having units of watt per hertz, W per hertz, and you can if you compare with the standardized SI units, you would see that the watt per hertz has the same dimension that that is of joules or energy. So is actually you can assume that this PSD is actually representative of the noise energy in that particular system. So these are the few terms that were used in this formula, in this problem. So now let us move on to the solution of this problem. First we start by identifying the given data. So we are given the value of bandwidth, which is 4 kilohertz, that means 4 into 10 raised to power 3 hertz. Signal power is also given, which is 0.1 milliwatt or 0.1 into 10 raised to power minus 3. We are not given the noise power, however we are given the noise power spectral density, and as I defined that power spectral density is power per unit bandwidth. So using this power spectral density, you can easily calculate the noise power by simply multiplying this power spectral density with the bandwidth. So the noise power in the system is actually equal to the noise power spectral density multiplied by the bandwidth. So if you multiply these two, you will get the value of 8 into 10 raised to power minus 9 watt. So if we use the Hartley-Shannon law, so I have used the version which uses the log to the base 10 because it's easier to calculate for us. So I have by using this log to the base 10 formula, C is equal to 3.32 B log to the base 10 of 1 plus S by N. So if you substitute the value, this B is given as 4 into 10 raised to power 3, signal power is given as 0.1 into 10 raised to power minus 3, and the noise power is given as 8 into 10 raised to power minus 9. And if we simplify this entire thing, so we will get the capacity to be equal to 54.4 into 10 raised to power minus 3 bits per second. So this channel can support the maximum information rate which goes up to 54.4 into 10 to the power 3 bits per second. So this concludes our discussion regarding the fundamental limitations which we started actually in our last lecture and concluded in this third lecture. And those fundamental limitations has been categorized as noise and bandwidth, and through those fundamental limitations we can identify the capacity of any communication channel by using the Hartley-Shannon law. Now we will start our discussion regarding another very important process in the communication systems, which is named as modulation. Modulation is a very important communication system process which actually is needed for most of the communication systems. So before describing what is modulation, I want to discuss why we need to modulate a signal, why the modulation is needed, and what is the purpose of employing modulation in any communication system. If you recall our discussion regarding the electromagnetic spectrum and the bandwidth, and we know that different types of medium and different types of channel, they support different frequencies for the propagation. For example, the wireless communication systems, they are generally used in the range of megahertz and gigahertz, whereas the wireline communication is done at the relatively low frequencies of the order of kilohertz. So if you are using a medium which has the if you are using a wireless medium for the propagation, in that case we cannot transmit the signal with low frequency. We have to transmit a signal which is of the order of megahertz frequencies. Second important thing that you should realize is that the messages, the commonly generated messages, they are generally at low frequencies. Take the example of voice signal, because it's a very common signal in the communication systems. The voice signal which is generated from a person and which is converted to electrical form by using a microphone, it generally contains the frequency contents up to 4 kilohertz. So the maximum frequencies in those voice signal is up to 4 kilohertz. And if I want to transmit this 4 kilohertz voice signal from the wireline signal, we can do that, because wireline, a copper wire can support the propagation at the low frequencies. But if we want to transmit the voice signal through a wireless medium like we do in the mobile communications, in that case we will not be able to transmit the voice signal from the wireless medium. Okay, because there is a mismatch between the properties of the signal and the channel. The signal is at low frequency and the channel is supports the propagation at high frequency. So the discussion that I want to elaborate, or the thing that I want to emphasize, is that in some applications there may be difference in the properties of the channel and the signal. A signal can be at low frequency, and channel that you are using that generally supports relatively high frequencies. So we need to change the frequency of the signal. So there is a need to have a high frequency signal to propagate through the other type of medium. Like if you want to send it through a wireless signal or coaxial cable, you need to have a high frequency signal. So the question is, how can we increase the frequency of the message signal? So of course, because our message signal is having a low frequency, is comprising of low frequency components, we cannot directly increase the frequency components of the message signal. Rather, what we can do, we can shift the message frequencies to a high frequency side. We make a frequency translation so that the overall frequencies of the signal goes to a relatively high frequency band. So how can we do that? We use a high frequency sinusoidal signal. So typically we use a high frequency sinusoidal signal which is named as a carrier. The carrier is something which actually carries the information. So what we do, we superimpose the information signal onto a carrier, and the carrier is at a high frequency, so that the overall frequencies of the signal becomes very high, and they becomes comparable to the frequencies that are supported by the channel. So by introducing a carrier in the propagation, we get a relatively high frequency signal that can be transmitted through a high frequency channel. So this process of introducing the carrier is actually named as modulation. So in modulation we use a carrier to make a frequency shift in the message signal so that it becomes suitable for propagation. Okay. So at this stage I want to define another term which is called a baseband signal. So generally, as I said, the message signal, they are low frequency signal. These low frequency signals, they are named as baseband signal. So baseband signal can only pass through a baseband channel which supports a low frequency only, and they cannot pass through a high frequency channel. So far I have tried to explain why we need the modulation. Modulation is actually used to transform the baseband signal to a high frequency signal so that it can pass through a specific type of channel. So concluding the discussion, I can say that modulation is the process that is used to make the information signal compatible with the medium. So by definition, modulation is the process of superimposing the message information onto a high frequency carrier. So in the modulation process, we superimpose the information signal onto a carrier so that it can be transmitted through a channel. The term modulation involves two waveforms. First is called a modulating signal, which is actually representing the message signal, which is a low frequency signal, and second is a carrier wave, which is actually a high frequency sinusoid. So as I said, the carrier is actually a sinusoidal wave of appropriate frequency, so that we can shift the frequency to the desired band. So what does a modulator do? So a modulator systematically alters the carrier wave in correspondence to the variation of the modulating signal. So basically the modulator changes the specific carrier in accordance to the information contained in the message signal, so that the modulated wave which comes out of the modulator, it carries the message information. So whatever is the output of the modulator, it actually comprises of two things. One is the information which is represented by the message signal, and the carrier wave. Because we use a continuous wave sinusoidal carrier in the modulation process, so generally the modulation that we use is named as continuous wave or CW modulation. So this is an illustration how does a modulator work. So we have a message signal which may be a voice signal. So we may have a voice signal which is converted to electrical form using a microphone. In order to increase the power, we sometimes use amplifier before transmission. So we have a baseband signal here. This baseband signal is fed into the modulator, and the other input to the modulator is actually the sinusoidal wave, which is generated by a high frequency oscillator. So it generates a sinusoidal wave, and modulator combines this baseband message signal and the carrier to generate a modulated wave or modulated carrier. This modulated carrier is transmitted by an antenna, and similarly at the receiver side this modulated wave would be received. If we think of receiver side, because we are interested in the information only, so in order to retrieve that information we have to reverse the process of modulation. So the receiver actually removes the carrier and recovers the original message signal. This process of removal of the carrier is named as demodulation, so that you can recover the original information. So modulation and demodulation are the counterparts of each other. Modulation is done at the transmitter side, where we introduce a high frequency carrier, and demodulation is done at the receiver side, where we remove that carrier to retrieve the original information. Sometimes, especially for the digital baseband communication systems, we use a different types of carrier, which is a periodic train of short pulses. So sometimes we use pulses as a carrier wave, but remember that these pulses cannot create a frequency shift. They cannot shift the frequency to a higher frequency. Rather, they are used to make a digital transmission. So they are used to convert the analog waveforms into a digital form. So this type of modulation is commonly known as pulse modulation, which is used in digital baseband transmission. But as I said, if this pulse modulation cannot create the frequency translation or frequency shift in the signal, therefore in most cases we need to combine both type of modulation scheme. So pulse modulation and CW modulations, they are combined together to make an efficient transmission in digital domain. this is an illustration of the modulation process through the waveform. So you can see that this first curve is actually representing information signal or message signal. From point of view of modulator, we call it a modulating signal. So you can see that it's relatively low variation represents that it is at a relatively low frequencies. So this is the message signal. When we are doing a CW modulation, we introduce a sinusoidal carrier, and that sinusoidal carrier is changed with respect to the amplitude of this information signal. So you can see that we have a sinusoidal carrier here, which is shown by this black line, and the amplitude of black lines is not constant. It's actually proportional to the amplitude of this modulating signal. You can see that this dotted line, actually this dotted line is just used to show that it's following the message signal. There is no physical dotted line here, so you can follow this dotted line. This is actually of the same shape as that of the modulating signal. So you can see that the amplitude of this sinusoidal carrier is systematically changed so that the envelope or these amplitudes, they represent the information signal. So this modulated sinusoidal carrier, which is represented by this black line, is actually carrying the information of the message signal in its amplitudes. Similarly, if you use a pulse modulation, you can see that the pulse train carrier can be used to represent the information. So we change this modulated signal, we multiply it with the short pulses, as represented here. We have a short pulses. So each pulse contains a portion of the amplitude represented by the message signal. You can see that the pulse amplitude, it follows the amplitude of the message signal. So if we can observe the amplitude of the pulses, we can retrieve the overall message information. So this is the representation of pulse modulation, which is typically done in the digital domain. Because we are using amplitudes to represent the information contained in the message signal, so this type of modulation scheme is named as modulation, amplitude modulation. So this one is actually continuous wave amplitude modulation, the B part, and the C part is named as pulse amplitude modulation, because we are using pulses and their amplitude to represent the information. So this is an example of pulse amplitude modulation. So summing up our discussion, we have talked about the modulation process, which is important in the communication systems. The modulation process is done to create a compatibility between the message signal and the overall communication system, so that our information can be propagated to a long distance in that particular communication system. Modulation is such an important process in the communication system that we will dedicate number of lectures in this course in describing different types of modulation schemes and how we achieve that modulation. So for the time being, I'll restrict to the introductory comments regarding the modulation, and we will be having further discussion regarding different types of modulation scheme, inshallah, in subsequent lectures. So we will stop here. Thank you all.